This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, your professor for this class, and this is Lecture 58 on lithography, where we have our second part of our two-part series on resolution enhancement technologies for lithography. Last time we talked about one of the three types of RETs in common use, optical proximity correction. This time I'd like to talk about the remaining two, off-axis illumination and phase shifting masks. We've seen a little bit about off-axis illumination in the past when we talked about how we illuminate a mask in a previous lecture. We have here diagrams of the different types of illumination shapes. The outer black circle represents the objective lens aperture or opening, and the source shape is shown relative to that objective lens size. Here you can think of this as the image of the source as it is projected into the objective lens using Koehler illumination. It's also the shape of the zero order of light for the case of a pattern of lines and spaces, for example. Our conventional illumination, or disc-shaped illumination, is illumination shaped like a circle. But we also have other shapes which you might notice do not have any on-axis components, that is, light going through the center of the lens. Without the on-axis component to our light, we call these illumination shapes off-axis illumination. And the three most popular shapes, besides conventional disc-shaped light, are annular illumination, quadrupole illumination, and dipole illumination. We won't really have any chance to go into the reasons why one shape is better than another, other than the very general idea that off-axis illumination can improve both resolution and depth of focus. So let's look at that. We have seen before that by tilting the illumination, we have the potential to switch from 3-beam interference, for the case of a repeating pattern of lines and spaces, to 2-beam interference, whenever the pitch of these patterns is small. We also have seen that with 2-beam imaging, the smallest pitch possible is 0.5 lambda over NA. That means the smallest half pitch that is possible is 0.25 lambda over NA. We derived that in a previous lecture. And we saw that this was twice as good as we could get from 3-beam imaging using coherent or normally incident illumination. So by properly tilting the illumination, we can double the resolution, improve the resolution by a factor of 2. But we also noted that when we use off-axis illumination, tilting the illumination, we always lose one of the first orders. That's the whole idea between 2-beam and 3-beam. We only have 2 diffracted orders going through the lens instead of 3. Because we've lost one of those diffracted orders, the quality of the image has gone down. There's less information about the image that's being projected into the wafer, and the result is a lower quality image. The quality, we noted in a previous lecture, is measured using something called the normalized image log slope, or the nils. And the nils controls exposure latitude. So by only using 2 beams instead of 3 to form our image, we have a lower nils, we have less exposure latitude. But it does allow us to have smaller images, smaller features that still form images, even though 2-beam images are not as high a quality. Well, it could be that we just live with this trade-off of lower quality for better resolution, except for there's one other advantage of off-axis illumination, which makes a big difference, and that is the impact on depth of focus. So let's look at tilted illumination, off-axis illumination again, and this time explore its influence on depth of focus. Here I show a picture we've seen before. We've got a mask with some lines and spaces on it. I'm going to illuminate this mask with light tilted at a particular angle so that the zero order lands in the lens right at this point. So these black lines down here represent the objective lens aperture or opening, so there's the edge of the lens, and we see that we're putting one of our diffracted orders near the right edge of the lens. Then for a given pitch, on this mask, we'll get a first order that lands here. The other first order will be lost because it will be out here somewhere. And we get two orders, or two-beam imaging. Now, what is the effective focus on this particular set of diffraction orders and on the particular image that we'll be making from these orders? Well, we also saw in a previous lecture that the effect of going out of focus was equivalent to saying that we're adding a phase error to the pupil function. That is, a phase error to the light as it comes out of the lens. And this phase error is symmetrical about the center of the lens and produces something that's close to a phase error, close to proportional to the square of the distance from the center of the lens. So the square of the spatial frequency, for example. Now, phase is relative. The only thing that matters with phase is the difference in the phase between two beams of light that are going to combine and interfere together to form an image. Here we're going to combine light coming from these two diffracted orders, interfering to create our image of lines and spaces. But it's only the difference between the phase of this order and the phase of this order that matters. Since let's now specify a little bit more clearly where these orders are. Since the phase error goes as the square of the distance from the center, we have to ask ourselves, where is the zero order compared to the center of the lens? Where is the first order compared to the center of the lens? Well, the position of the zero order is controlled by the angle of the illumination. If I bring my light down at a particular angle, then it lands at a particular spot right here. That's where the zero order is, controlled by the illumination angle. The first order, on the other hand, is controlled by the pitch. Right? The distance from the zero to the first order is going to be a spatial frequency distance of 1 over the pitch. So if I tilt at a particular angle and I print with a particular pitch, I can adjust the position of the zero and first order to be an equal distance about the center of the lens. Now, suppose I do that. The first order and zero order are the same distance from the center. If the phase is a function of the distance from the center of the lens, putting them in those positions means I get the same phase error for the zero order as I do for the first order. If I have the same phase error, I have no phase difference. Without a phase difference, I will not get any degradation due to being out of focus. Ideally, I can actually achieve infinite depth of focus with this arrangement. Now, practically, though, we can never quite, can never come close to an infinite depth of focus. But by placing the zero and first diffracted orders the same distance from the center of the lens, we can minimize the impact of focus errors on the image. Now, an important thing is this DOF is maximized only for one pitch. Right? If I change the pitch, what happens? This first order starts moving to a different location. And only at one pitch will this order be the same distance from the center of the lens as my zero order. So what do? I tilt the illumination so that I get this ideal lack of sensitivity to focus errors for one pitch. I have to optimize my illumination to give me the best possible results for a single pitch. Here's an example of how that might work. What I show here is the nils. Nils is the normalized image log slope. It's the quality of the image. It's the slope of the image. So high nils means I have really sharp images, and low nils means I have very poor quality images with low slopes. And then I show here how that nils degrades as I go out of focus. So on the x-axis, I plot defocus distance. Now, I'm going to compare two types of illumination. A conventional illumination with sigma of 0.5 and an optimized dipole illumination. Dipole means I'm simply tilting the light at a single angle. And let's see what the results are going to be. I've optimized the dipole so that I achieve that result that I want to achieve for this particular pitch. Right, and here you can see I'm using 120 nanometer lines and spaces, chrome on glass mask. We'll talk about phase shifting masks later. A particular NA and a particular wavelength. Now, the first thing I might notice is that when I am in focus, the defocus distance is 0. What happens to my image when I switch from conventional to dipole or tilted illumination? I see that the quality of the image is reduced. This is exactly what we said would happen. I'm losing one of the first diffracted orders, and so the nils, the quality of the image, goes down because of that. However, because I'm using this optimized tilted illumination, the 0 and the first order about an equal distance away from the center of the lens, I have minimum sensitivity to focus errors. And when I go out of focus for my conventional illumination, the quality of the image crashes, so that only a very small amount of defocus gives me very bad images. Eventually my image disappears completely, where if the nils is 0, that means I have no information about what should be a line and what should be a space. On the other hand, by using the tilted illumination, this dipole illumination, I see that my image degrades very slowly as I go out of focus. I can go out of focus for a long, long ways and still get a very good image. This is the advantage of the dipole illumination, or the optimized off-axis illumination. Out-of-focus image quality is improved. So now the trade-off is very different than what we thought before. Now I'm not just getting higher resolution. I'm getting higher resolution with improved depth of focus, which is really what we want. Printing small features that have very low depth of focus may not be a big advantage for us, but printing small features with big depth of focus, that's fabulous. This is exactly what we want in lithography. Why off-axis illumination is almost universally used today when printing high-resolution features. It's extremely important in the industry. An important caveat, though, we can only optimize our illumination for a particular pitch. And that means we have trouble printing high-resolution features at multiple pitches at the same time. Another approach, which in one sense accomplishes the same thing as off-axis illumination, but without the pitch sensitivity, is phase shifting masks. Let's look at what a phase shifting mask is. Well, light has both amplitude and phase. We know that. And we know that phase influences how light interferes. If I have two beams of light that are in phase, they add constructively. If I have two beams of light that are out of phase, they add destructively to give us darkness. And if we have a standard chrome on glass mask, the thing we've talked about so far in this class, we're modulating only the amplitude of the transmitted light. Well, we've got chrome, and makes the amplitude of the transmitted light go to 0. And we have glass, where the amplitude of the transmitted light is about 1. So we're only modulating the amplitude. What if, instead of modulating just the amplitude, we also modulated the phase of the light as it was transmitted through the mask? If that happens, we call it a phase shifting mask. This idea was first developed by Mark Levinson when he was at IBM, and first published in 1982. It has the ability to switch from 3-beam to 2-beam imaging, just like off-axis illumination does. However, we don't have to optimize for a particular pitch. This phase shifting mask approach can give us 2-beam imaging for any pitch, where each diffracted order is an equal distance from the center of the lens, and we get optimum depth of focus behavior for any pitch, not just one pitch. Very, very promising. Let's look at how we can make a phase shift. So let's start with a mask blank that we're going to illuminate with light of some wavelength lambda. Now, instead of putting chrome features like we've been doing so far, let me put a block of glass on top of the mask blank. In fact, I'll make this glass have the exact same optical properties as the mask blank. It'll be the same material. And this glass will have some thickness T, and refractive index n. Now, as a reference, the air in the region where I'm not putting an extra piece of glass on top of my glass blank, the air will have an index of 1, a refractive index of 1. Now, let's shine some light through the region where I didn't put my extra thickness of glass. What's going to happen? Well, light, as it's traveling through the mask blank, has a wavelength that's reduced by the refractive index. So if the wavelength is 193 and my refractive index is n, then the wavelength inside of the mask blank will be 193 divided by n. So it's reduced by the factor of the refractive index. So once that light comes out, it starts having the vacuum wavelength, the wavelength in air, because the index is 1. I go back to a wavelength of, say, 193. Now, consider light that's traveling this time through the mask and through this extra thickness of glass that we've added. Here, the wavelength remains reduced by a factor of n. So this light, as it travels through the glass, undergoes a different phase change than the light that's going through the air. There will be a phase difference between the light that didn't go through this extra thickness of glass and the light that did. How much is the phase difference? Well, we know that light undergoes 2 pi of phase, 360 degrees of phase, every wavelength. And the wavelength is the wavelength inside of the material. So we can convert from thickness to phase by simply taking the thickness and multiplying it by 2 pi and divided by the wavelength inside the material, which is the vacuum wavelength divided by the refractive index. So what's the phase difference between these two beams of light going to be? Well, I simply subtract the two phases as it traveled through an equal distance t. Here we go through this distance t with an index of 1. Here we go through this distance t with an index of n. So the phase difference will be 2 pi divided by lambda multiplied by t and then multiplied by the refractive index difference, n minus 1. This is the phase shift of the light going through the glass versus the light going through the air. In fact, we'll call this extra bit of glass the phase shift material, because, and this will be the phase shifted region of the mask. What we're going to do is phase shift by 180 degrees. That's going to be our goal. You can imagine why we're going to do that. If light is phase shifted by 180 degrees, and then we add the two beams of light together, we'll get darkness. And that's going to be our goal. Taking light that's not phase shifted, combining it with light that's phase shifted by exactly 180 degrees, adding them together to cancel out and get darkness. To get a 180 degree or pi phase shift, the thickness of this phase shift material, T, must be lambda over 2 times this difference in refractive indices. The refractive index of our fused silica, or our glass, is on the order of 1.5, thereabouts. So you can see that the thickness that we're going to need to add is on the order of the wavelength, the vacuum wavelength of light. Well, if we have this ability now to shift the phase of light by 180 degrees where we want it to be shifted, how can we use that? Consider a mask pattern of just 2 spaces that are close to each other. So I've got a slit or a space. This is a cross section of the mask. I have a slit here, and next to another slit here, and then chrome on either side, and a small line in between. This would be a standard chrome on glass mask here. Now, for my phase shifting mask, I'm going to simply add a region of glass on top. This glass will have the same refractive index as my blank, so we don't have to worry about reflections in here at all. But it will be adjusted in thickness to give exactly a pi phase shift, 180 degree phase shift. Now let's consider, when we illuminate this mask, what the resulting images are going to look like. Well, the first thing we're going to need to know is the mask transmittance. For chrome on glass mask, we've always assumed a very simple mask transmittance of 0, 1, 0. 0 underneath the chrome, 1 underneath the glass. The electric field as it's transmitted through the mask is simply the 0, 1 function. Now let's look at what it looks like for our phase shifted mask. Underneath the chrome it's still 0, underneath the glass it's still 1, but underneath the phase shifted chrome it is 1 but shifted by 180 degrees. From an electric field perspective, we can call that -1, an amplitude of -1 in the phase shifted region. So we have 1 and a -1. Now we can take the Fourier transform of this, we can pupil filter it with our lens, cut off the high diffracted orders, and then calculate the image at the wafer plane. The electric field at the wafer plane will look something like this. Unfortunately, if we have a very high resolution line between my two spaces, it doesn't get all the way to darkness, not to 0. Light diffracts underneath this chrome line from both spaces. The resulting electric field at the wafer is higher than 0. The chrome line doesn't achieve perfect darkness. But what happens here? Light diffracts from this space and from this space, and when they combine at the wafer, the light coming from this space is 180 degrees out of phase with the light coming from this space, and so there'll be a point underneath this chrome line where the electric field goes to 0. Another way to think of it is the electric field goes from +1 to -1, and even when I smear it out, to get from +1 to -1, it has to go through 0. So there's a point where the electric field goes to 0. Now, when I square the amplitude of that electric field, I get the intensity of the image at the wafer. And the resulting intensity in this small line region is brighter than it is in a chrome on glass case than when I use the phase shifting mask case. I can make the darkness darker with the phase shifting mask. I use interference to create darkness, and this destructive interference allows me to make a dark line darker than it could be otherwise. And this is the key to how a phase shifting mask works. Now we could also look at the diffraction pattern for periodic lines and spaces where every other space is shifted, which is the approach we're using here. I'll leave that as an exercise we might do for homework. But what we would see is that the 0 order goes away. The 0 order goes away because every other space produces 0 order light that is phase shifted by 180 degrees, and all of the 0 order light ends up canceling out with each other. So we end up with no 0 order at all, just a +1 and a -1 order, and that results in two-beam imaging. So we can get with the phase shifting mask the same advantages that we can get with off-axis illumination, two-beam imaging, but I don't have to optimize for a particular pitch. This works for any pitch. So how do we use the phase shift? We adjust the shifter to give us a 180 degree phase. That means we adjust the thickness of that shifter. And then we combine shifted and unshifted light to produce darkness where we need it. Phase shifting masks are very good at creating small dark features, and that's what we use it for. Small bright features are much harder. Contact holes are small bright features, and it's very hard to use phase shifting masks to improve the imaging of contact holes, but to improve the imaging of lines, we can do that. There are lots of types of phase shifting masks. The one we just looked at is called an alternating or Levinson phase shifting mask, where every other space is phase shifted by 180 degrees. A few others that we won't spend any time talking about are chromeless phase shifting masks, where we simply use a phase edge. One side is phase shifted, the other side is not phase shifted, and that phase edge will print as a small dark line because of that destructive interference right at the edge. Rim shifters put a phase edge on the outside of a feature, but by far the most common and most commonly used phase shifting mask today is called the attenuated or embedded phase shifting mask. Here we embed the phase shifting property into the absorber. Now, our chrome on glass mask uses chrome as the absorber, but for an embedded or attenuated phase shifting mask we use molybdenum silicide as our absorber. And the absorber is not perfect, intentionally made to be not perfect. In other words, we allow that absorber to transmit some light. About 6 to 9% of the light that's incident on it is transmitted. So now I've got a clear region that transmits 100% of the light, and a dark feature, dark in quotes here. It's darker, but it's not completely dark. This dark feature transmits about 6 or 9% of the intensity of the light. So that's the intensity transmittance of 6 or 9%. But we have that transmitted light be 180 degrees out of phase compared to the clear regions, so that when the light transmitted through that feature interferes with the light coming from the space, we get darkness that is darker than we could get with chrome. Now, this all sounds great, and alternating phase shifting masks enable two-beam imaging with optimum depth of focus, just like off-axis illumination, except it works for any pitch, not just one pitch. Here's a problem, though. The main problem with the alternating phase shifting mask is something called the phase conflict problem. So, the way we make a phase shifting mask work is we put a line with 0 degree phase on one side and 180 degree phase on the other side. In other words, this line will have a nice high resolution, good depth of focus, because I have 0 degree shifting of the light coming through the glass on this side, and 180 degree phase shifting of the light coming through on this side. And when the light leaks underneath this dark line, the light cancels out, and so it stays dark, and I get good imaging. The problem is, if I have an arbitrary mask layout, I will run into phase conflicts. That is, if I have an odd number of lines, here I show 1, 2, and 3 lines, I start coloring this mask with the 0, 180. I find that I cannot make all of these lines have the proper phase shift. So here on this line, I have 0 and 180 on either side, so I get darkness, a good dark feature here. On this line, I get 0 and 180 on either side, so I get good resolution on this line. But look at this line on the right top. I see 180 on one side and 180 on the other side. This is a phase conflict, and the phase conflict means that this feature will not print well compared to the others. Well, this is a real problem. With arbitrary layouts, I will run into these kinds of phase conflicts, probably quite frequently. So we have to have restrictions that say you cannot have a simple T pattern like this, for example, because there's an odd number of phase regions. But it's very hard to lay out our chips the way we want them to be and avoid all of these phase conflicts. We're still trying to figure out how to make that work, to create design tools that can automatically ensure that we never have these phase conflicts. And they're not perfect yet. For that reason, we have found that alternating phase shifting masks, while it has many advantages over off-axis illumination, still is not used as frequently because of this phase conflict problem. All right, we've looked at 2 more types of resolution enhancement technologies. Let's review what we have learned. As always, you should be able to quickly and easily answer these questions. If not, you need to go back and review the material. What are the 3 main RET approaches? How does off-axis illumination improve resolution? How does off-axis illumination improve depth of focus? What phase shift do you want in a mask if you want to produce destructive interference? And finally, which PSM approach is most common in manufacturing today? Oh, one more. Explain the phase conflict problem for alternating PSM. Well, that's our lecture on OAI and PSM, and our last lecture on resolution enhancement technologies. Until next time.